and you know what are the concepts. Because we for the one okay. Start. I mean, everyone who's too late has to learn it the hard way.
Seem to be 11 people. The hike, maybe someone. What about
Peter is missing, but well,
you know Peter?
yeah, when he was here.
Hey, all the people are staying at top rooms. Hotels.
Right, all of them are missing. Maybe we wait for us. There was yeah, after the group. Good. Yeah. I think I do some.
Well, I have a principle of not waiting so that people do not come later tomorrow, but earlier.
Someone coming? Yeah. Yeah. Good. Okay. So the topic of my talk is cohomology, and maybe we will expand the topic if there's demand. So I optimistically call it Cohomology 1. And I want to start by repeating a couple of things. So Matthias talked about schemes on Monday, and one of the important things to know is what open subsets are to even define a scheme. So I will briefly remind you of that. So let P be a proposition, then we can define when it is an open or enclosed proposition, and P is open means there exist elements in our base ring, such that the proposition is equivalent to one of those being non-zero. And as Matthias showed us, being non-zero is the same thing as being invertible, so we could have taken also that. And yeah, P closed is analogous. So we have some elements in the base ring such that P is equivalent to all of them being zero. Good. Can anybody, everybody read what these things mean? Good. Yeah. Okay. And with this notion of open, it's possible to define a scheme, which was a type with a finite cover by affine schemes. And affine schemes were defined like this.
That's one thing. I think it's the remark that an open is a complement of a closed is important here, right? Because we repeat what we learned yesterday about non-zero vectors, and this way one can see that the double complement of something open is again open.
Is this what open propositions are double negation state?
Yeah.
So you get this problem in terms of complements and propositions. You can say if you have a closed proposition, the negation of this will be an open proposition.
That was the thing, you know.
So closed is somehow a bit more fundamental, I would just say.
Yeah. I mean, it's certainly asymmetric in a way that might be unexpected. If we can negate something closed and get something open, but negating something open is, something.
Unexpected from the point of view of differential geometry, where there's no difference between opens and closed. We can always take the complement, pass from one to the other in classical differential geometry. But in algebraic geometry, of course, we're used that there are lots of closed schemes, closed subscheme structures from the same closed topological subset. And this, nice reflex in that.
Yeah.
Right, because the complement of two closed propositions can be the same open proposition, even though the two closed propositions were not the same.
Yeah, for instance, the two closed ones, x equals 0 and x squared equals 0, they have the same complement.
What is the question?
So I was just asking if there was an analogy of this, the complement of an open is not necessarily closed.
So analogy where
In classical algebra.
Well,
Because English just gave a nice example.
Yeah.
Maybe hidden.
well, the notion of complement is a more nuanced one than simply taking the complement of the subset of points.
So generally in constructive mathematics, I think the word pseudo complement is more appropriate for negating a proposition or for taking the points that are not in some subset, because doing it again doesn't necessarily give us the same thing again. So it's not really a complement, but really builds a complement for short legs.
And we are used to, at least in classical math, if you have some subset and you negate it, you might think, or you're used to thinking that the union of everything, intersection is empty, and that is still true, the former not. It's important to keep in mind.
So now with the example Lucas might have been looking for, if you start with a closed proposition x equals 0 and take the pseudo complement, then you obtain the open proposition that x is not 0. And if you take the pseudo complement again, then you obtain the proposition that x is nilpotent, which is an infinite union of lots and lots of closed subsets, then the x equals 0, x squared equals 0, and so on and so forth. But so it's more than just one of those.
There's a kind of, in algebraic geometry, when one considers the reduced close, I can always take the reduced structure, but here I have something like the maximum.
Exactly.
Whatever it is, it's not a scheme.
One can conjecture that the complement of an open in a scheme is like a formal scheme or the formal completion of a closed, but we never went really into that. But I would say that's probably true. Yeah, okay.
Yeah, so, sorry for taking this detour.
I think it's really.
It's at the core of the proof on the Serre-Ranching theory. There we need exactly these kind of considerations already in the very beginning of the good detour.
Okay, so just a brief reminder. We defined the spectrum last time as homomorphisms from some finitely presented R algebra A, which is kind of what we always assume. And yeah, so let me write it once. And yeah,
So it's a modulum of algebra.
yeah, right. That's not enough to write, because it could also be a morphism of R modules that way, I guess. So yeah, I should be more precise. And what did I want to remind you of? Something. Okay. So one important principle I think that wasn't mentioned is that schemes are dependent sum laws. So
No, that has nothing to do with you.
okay. So that means we've seen this dependent sum construction from homotopy type theory, which is the operation of taking a dependent type, some fixed type, and constructing the total space. So I do this dependent type as some varying vibration or a fiber of some map, which goes down from the total space. So I can construct the total space, and turns out that when my base is a scheme and all my dependent types are schemes, then this will be a scheme again. And if I now use open and closed propositions to define open and closed subsets, I can immediately see that those are schemes. So here I can actually see directly that these are examples of schemes. So schemes, let's just keep it simple.
So what is sigma?
For the upper one, we don't know yet, I guess, but for that one, you can write down the algebra, because this proposition will be the spec of R modulo the ideal generated by all these numbers.
Schemes are sigma.
What is the sigma type? You asked what is the sigma there? Sigma goes the sigma type. So
Dependent sum, was it called?
depending on minus. So this means if you have a scheme and you have something over it, such that all the fibers are schemes, then the total space is a scheme. So sigma, you can geometrically, sigma means take the total space of the fibers.
Okay. So maybe to write it down in a bit more details. So, scheme, and for all point in the scheme, I have a scheme by X. Then I write the sigma type like this. Maybe it's easier to recognize from memory. This is the notation for a sigma type, and this will be a scheme. Okay, so these happen to be examples of schemes which are sub-schemes of the point. And in some sense, we have lots of those. So that's probably something which needs a bit getting used to, but a lot of things in synthetic algebraic geometry take place below the point, so in smaller spaces. And we have a lot of propositions which happen to be schemes. Okay, so I don't know if Matthias, I guess Matthias told us that, but a subset of something is open if it's pointwise an open proposition, and it's closed if it's pointwise a closed proposition. And if we want to have this subset as a type, not as a predicate on some type, we can take the sigma type of it. So I have some scheme and some open proposition U, so X scheme, sorry, and U of X open for all X, then this thing is a scheme again. And the same for closed, of course. So this gives us, for example, if I have closed subsets of Pn, which Matthias defined on Monday, then these will be schemes again. And this gives us lots of examples because it means we can take Pn and cut out some subspace using equations. Because at any point, these equations will ask for some numbers being 0. And so it's pointwise closed. Therefore, it gives us a closed subspace.
So you just proved that closed subset of the scheme is the scheme by using the proposition that sigmatizes is the scheme.
Yeah.
Okay. Good.
Why not? Yeah. And I mean, what is also kind of a bit weird from a classical point of view is that if you have 2 points in some scheme, then the type X equals Y is a scheme. And important to note, and it is a closed proposition if, for example, X is affine. And there's a kind of easy proof of that, if you're already in the subject. So you know, being closed itself is a proposition because we truncated it. Saying exists here, this whole thing is truncated. And that means if we want to show a proposition, we can unpack any thing we only have merely, where we only have existed. But for affine schemes, which are come from finitely presented algebras, we know that there exists a finite presentation of this algebra, and this finite presentation F, because I used P already so much. And this finite presentation gives us an embedding into a fine space. So if I have this finite presentation, I also have that spec A is a subset of R to the n, which we also call AN, to look like we're doing classical things, or to point at the connection to the classical things. Why? Because when I have this presentation, I can just rewrite, as Matthias showed us, our the type of HOMs I can then rewrite using this universal properties to common zeros. Yeah, and here I have described directly a subspace of a fine standard space. So I merely know that I have a subspace of a fine standard space. And what did I want to do again? I wanted to show this is closed. And now I can rewrite X equals Y as sums of coordinates here being 0, differences, sorry, yeah. Differences of coordinates being 0. So I have n numbers which should be 0, and that's exactly what a closed proposition is. So it's good. Yeah, so, but in general, it's still a scheme. So what happens, just to give you a rough idea, if I have some open covering, might happen that I have to say something if this point is in this part of the cover and so on, but that in the end will be open things. So I get something like something closed in an open, which doesn't have to be closed on its own. So in general, you have to say scheme. And but there are interesting schemes where that are not affine, but this is closed anyway. For example, projective space has this property. And in general, we call such schemes separated because we think it matches with the classical notion. Okay, so yeah, but what this means is also that pullbacks of schemes are schemes again, because a pullback is an iterated sigma over the equality type. So you already know this stuff from Hot. So this gives you also a scheme again, but otherwise just note yeah, pullback clause.
Could you give a real example of a term of type Pn, where I would apply this expression?
But
I'm wondering now, how would you get these xy's from some scheme? It's not exactly, it's not affine.
Okay. I mean, in Pn, we can use homogeneous coordinates, for example. So we could have something like this and something like this. And those being closed, those being equal, means that all 2 by 2 minors are 0, I think, which is a bit of a trick one has to think about for a second. I don't know, was there some easier immediate thing to see it? But yeah, so I mean, let's say it like this. This equivalent, this is equivalent to all, yeah, I'll just write it down, all 2 by 2 minus in this thing.
I mean, this is the most obvious thing if you know linear algebra.
Mark, it's the most.
Yeah, I mean, that's the rank 1 condition on the matrix. So it's
yeah, I mean sure, it
one
just is a reformulation. Yeah.
I mean, of course, one has to prove that this is does not depend on the representation. So if you scale the x's or the y's individually, but this is,
yeah. If you had almost nothing to do with linear algebra for 10 years, and someone tells you this, you think, oh, this is a cool trick. So it works for me. Yeah. But yeah, it's just a reformulation for linear dependence. You might remember from your linear algebra courses.
I mean, it is interesting, logically speaking, because the second statement is an equational statement, and the first one is an existential. Right.
By definition, the first one says there exists a number that's scaling
right
by that number is y.
Yeah.
So we convert a sigma 1 statement to a sigma 0 statement.
It is a bit surprising. Yeah.
Is the quality of elements of R quantifier free for you?
Yes. I know what you mean, but yes, it is perfect.
Okay, and I mean it is quite useful because we have results for separated schemes for ones that I think we have closed ones are separated again. that should be true. And what we definitely checked once is that for affine covers of something separated, the intersections of the cover are affine. And I mean, that also comes from, I guess, the fact that we are always quasi-compact, quasi-separated. I don't know. No, maybe, no. Probably doesn't have to do something with each other. Yeah, but you looked so surprised. General, yeah, good. So I was questioning what I'm saying, but yeah.
And it should always go to n, right? That should be n and m, or n equals m.
That's an n, and that's also an n.
Thank you.
And also all n's.
Yeah, n and m on beta variables standing for the same.
That's why I used L.
Because for him, it's two writings of the same letter.
Okay, now we've remembered a couple of schemes, and what is also important in algebraic geometry are sheaves of modules, say, on schemes. And that's a bit different for us, but maybe not much. I don't know. I'm very used to it now, thinking this way. So first, preliminary definition. I will always call R mod the type of R modules. So type of R modules, which means exactly the usual. You have an abelian group, so you can all just write that down in multiple type theory. No problems. And then we define kind of our analog of sheaf of modules, which is probably more and different in general, but yeah, pretty practical to work off. And we often call those things bundles, which I guess gives some good intuition of R modules on some type X are maps from X to this type of R modules. So this type, due to hot, also behaves like a modular stack which you usually have. So here you have a way to represent also maps whose fibers are R modules in a non-Mealy sense. And yeah, so you can imagine over each point, we have some R module. Okay, and what was important? Yeah, okay. So, and yeah, for the structure sheaf, we just take one trivial thing. So the map like this, or bundle of R modules like this, where you just take R over itself as an R module, is the structure sheaf. I mean, we call it the structure sheaf to make the connection to the classical setup. But yeah, it's a bit weird because we don't call the underlying object sheaf. Okay, and
that's the trivial bundle with fiber R. Looks pretty. So
This is a trivial.
yeah,
Yeah.
it is.
The
Yeah.
structure sheaf.
The structure sheaf is it the same as assigned the open subset, the sections in the trivial bundle?
yeah, okay, that's good.
Yes.
Yeah, it's a bit weird. I mean, you have, for example, you have the global sections of the structure sheaf.
Yeah.
So let's say if this is affine R by our axioms, again, this. So this is also a reminder, like was like this on the slides of Matthias. But this is one justification for calling this structure sheaf.
Do we have a size issue here? So.
No.
If you take- No, it's a serious question. So if you take the type of all bundles are, then it's in universe I+1, right? Okay.
Yeah, but I mean,
In the same universe where the type of all R modules is.
yeah.
Right?
Do you agree?
But
But you're one level higher than R module. The bundle of R modules.
Than a specific R module.
So, I mean, it depends in which universe you are.
Yes, okay.
One higher than where.
Yeah.
R.
if R is in UI, this is in UI+1 or higher if you want to.
As you would expect.
Okay, and balance is now again in UI+1.
The type of bundles is in UI+1.
But every specific bundle will be in UI.
UI.
Yeah.
Okay,
But that's something that will never bother you.
Yeah.
At least it didn't bother us so far. Well, I mean, maybe once we formalize all of this, also these parts, then we will worry about it, but I don't think so actually. Because this is like a common move you make a lot. And okay, so what you can do with some bundle, like right on the typing, with some bundle, R modules, and an open subset of X, or actually any other subset. We can define some kind of sheaf-like evaluation on the subset by just saying, well, these are the global sections on some subset. So this is maybe how one wants to go into the sheaf direction, which is sometimes a good move. Okay. Yeah, and how this evaluation and localization, which usually in algebraic geometry gives you also the restriction of the structure sheaf, how this behaves is important for cohomology. At least we need a little bit about that. And the following proposition is concerned with some part of this. So let me look up the right formulation. Yeah. So if you have a bundle of modules, sorry, and X is a scheme, then what did I want to say? Okay, right. What might be also good to know here is this is now a module over the algebra of global functions on U instead of just R. It's also still an R module, but I guess this is good to know, or maybe like this. R to the U module. Okay, and if you have an R to the X module here, you can take some function and localize this module at this function. And it turns out that this is the same as localizing pointwise. So I also like to write this sometimes for application. So you take the module at each point and localize by the value of the function that you use here to localize the whole thing. But what I kind of sweeping under the rug here is that we need all three axioms to prove this, because there's some pointwise global principle behind it, but yeah, let's not worry about it. Okay, but that's something you can do. And considering this, if you want to know something like restricting to an open subset is the same as localizing, you can just ask it pointwise. Ah, yeah, and now I see, forgot to hand out some names here. So I guess I should write it like this. So in general, maybe with an R. In general, for R in R, we call this the proposition either that R is invertible or that R is different from 0. And here we have an OR of propositions like this, just to talk a bit about it. A general open is an OR of those things, and a standard open. So this is a standard open proposition. So this form, and so you can view this as the simplest open subsets of the point. And yeah. I also want to define, I guess I don't remember it from my way. It didn't happen, or I should remind everyone anyway. So in general, you can define a standard open subset as one way is the points where some function is non-zero. Or invertible. Or you just write down what it is as an affine scheme. So this works like you might know from classical algebraic geometry. Okay, and with this here, this is an open proposition, so you can see this is also like a subset, and at every point it is an open proposition, so it's an open subset. Standard open subset. Okay. And so what we want in general is some subtype of our modules which behaves well enough to with respect to localization and restricting that we can do some reasoning about cohomology. And what it turns out is enough is that we can switch this localization with restriction. And it's already enough to know something like this pointwise. So we can define first a nice type of R modules, which we call weakly quasi-coherent. I guess I should at least write it out once. And we always abbreviate it with WQC. And we call it that if for all elements of R, M localized at R is the same as M to the dr. And here I'm not really asking for given equalities, but I want to be a canonical map to be an equality, which we never talked about, but something canonical can also try to reproduce for yourself, which comes from the general fact that this equation holds. And yeah, for the tensoring here, you take the one element localization. So this is the map from, but let's just believe it's something canonical. And we can ask this pointwise. Okay.
What is the weekly referring to?
History, I guess. I mean, there's also a notion of strongly quasi-coherent, and then we came to use some weaker form of that, which actually works better for this application, and which also gives you an abelian category of modules. So yeah, but the notions, I would say, are just history, and I don't actually know, maybe someone does, how it relates to actual quasi-coherent modules from algebra exchange.
It's a classical external quasi-coherence on each slice.
What is weak or strong?
Weak. To be more precise, so what is the model? So I don't know that fancy cubical model. We will learn about that in Matthias' talk. But what's the one categorical model? It's the Zariski topos of a base scheme, base ring. And we call a sheaf in the Zariski topos of a base scheme can be restricted to lots of individual sheaves, one for each scheme over the base scheme, locally defined representation. And then the characterization is following. An object of the Zariski topos is WQC, if and only if all those restrictions are individually quasi-coherent, as interpreted as ordinary sheaves on the on those ordinary schemes. So in the little Zariski sense. But unlike strong quasi-coherence, there's no regularity, Gleichmäßigkeit, between those restricted sheaves. So they don't originate from one sheaf on the base scheme. Instead, like on each, there can be a different one. So we don't have that full stability. In case people are interested, we can also write it up.
Yeah.
First is M tensor A equals M to the power spec A. So is this
Yeah, we can.
condition or?
No, I was saying there's a general fact like this. And you can look at this to find out what the canonical map here is.
But this holds for any one.
No.
The thing in brackets is exactly, so it's not yet well specified because it's unclear what A is, capital A.
Yeah.
But if you ask the thing in brackets to hold for every finite percentage R algebra A, then you have exactly the strong quasi-coherent switch.
Yeah.
And if you just ask it for the algebras of the form R localized away from a single R, then you obtain the WQC.
Yeah, but I mean, we always have a map, a canonical one.
Yeah,
and
but
that's
you wrote equals not a map. So
yeah. Okay.
But I mean, in this special case, you can also say it's just the map coming from the universal property of the localization.
Yeah.
Of M to R.
Checking that on the
Yeah.
right hand side, R became inverted.
Yeah. But I mean, I find it actually easier to look at this map. But yeah. You can.
But I think
also do it that way.
Didn't get everything equals set. So what did you mean by saying that things come not from a, so you start with a sheaf on one slice and then you can restrict it to smaller slices?
Yeah.
Okay, but then all these restrictions come from one slice.
Yes, that is true.
Yeah.
But perhaps they don't come from a single sheet on the little Zerisvitopos of the base.
Ah, okay. Yeah, so they are defined on some stage,
Mhm.
and on this stage, yeah, okay.
So, I mean, what is important for the following from
So they can change
this,
they can change the format.
Okay, doesn't make it sound like that, right?
So I think about it.
okay, so what's important for the following is that if we have a bundle of, let's say, on a fine scheme of weakly quasi-coherent modules, we know that the module of global sections on some standard open is the same as a localized array. I mean, that's something you would usually just have, and here we make a definition that allows you to reproduce that.
Would it be M localized array?
M localized array, thank you. Yeah. Yeah.
What do you
Okay. Huh? Mean with what?
How can you localize?
M is an A module. Ah, okay. This is a bit too wild, I guess. Oh,
Okay. That makes more sense.
okay. Take the module of global sections, localize that. Okay, and now we did enough on the geometry side to actually calculate something with cohomology. But before we calculate, I should tell you what it is. So this is kind of a new chapter, cohomology, and you start with a proposition which is just from homotopy type theory. So if we have A an abelian group, then there is for any n natural a type An, which is called the Eilenberg-MacLane space, such that, or this is actually part of the datum, or that is pointed by star connected, which means for all x in this type, x is equal to star, but only nearly. If I don't have this propositional truncation here, it's contractible, contraction center star. But in this case, it just means homotopically connected as a higher type. And yeah, okay, then I should actually say n greater 0 if I do it like this, but those are all interesting cases anyway. And I want this one to be a de-looping of my abelian group. which means the n-fold loop space of KAM could be isomorphic as a group to A. And what does this mean? This is also just a notion from homotopy type theory. So the loop space of some pointer type is just the equality type at the point. And when I take the loop space, it is naturally pointed again by the reflexivity equality. So I can iterate the loop space. And I can also show in homotopy type theory that this loop space always has some wild group structure. And yeah, I don't know, no, in this case, I don't have applied it. And if I ask this, I also know this type will be n-truncated, because it means if I take loops n times, I kind of reduce the homotopy level of the whole thing each time. And in the end, I arrive at 0 at sets, because a Abelian group entails here that it is 0 truncated. So in total, it means that has to be an n-truncated type, which is connected and pointed. So these things just exist in homotopy type theory, and we can use them to define cohomology in a very pleasant way.
Right, you need connectedness because condition C does only see the connected component of star.
Yeah,
So for
if I want something unique, I certainly need connectedness.
yeah, and if you want to say something about n equals 0, then you just drop condition B.
So I want, yeah, I should drop condition B then, but yeah. But I mean, yeah, for any integral 0, it's just A itself.
You want a group structure on the field. So then 0 and A, B, and C. We see as a read says
KAN is A, yeah.
yeah, this thing of passive group structure is supposed to be as more to A, but in the case n equals 0, the group space does not have a group structure. So it is a bit different.
Maybe I should.
No, really. Or no, maybe that's how I actually work. But the equation is certainly what you want. A 0 equals A.
Yeah. Well, I mean, for n equals 1, you just have to walk on one B equals.
Yeah.
So that now you have a morphism of sets. Conditions.
Yeah, Lucas.
Maybe I missed that. Would you want this to be n minus 1 connected?
You get it.
That's the consequence.
I thought this was the character.
I mean, it would be a bit more natural to ask for n minus 1 connectedness, I guess. Or
yeah, okay.
Ah,
Is it
okay.
the
This
same?
also has then for the n equals 0 case.
yeah,
Okay.
then it just means inhabited. Minus 1 connected. But I mean, yeah. Today we only need this anyway. And
Yeah.
lots of times it's better to think of this. I don't know. Yeah. But it's a bit more natural to say n minus 1 connected. Okay. So definition. N is a bundle of R modules, or maybe for this definition, just say it's a bundle of Abelian groups. And if you plug in an R module in this definition, you just forget the R module structure. It's a bit sad, but how we do it right now. Yeah, and some number. Yeah, I guess I do it like this. I also say A is equal plus A. I can define the cohomology with coefficients in M to be the set truncation of just this pi type.
MX.
Anyways. Thanks. Okay, and I mean a couple of things kind of follow more or less directly, like what you expect, like functoriality and being able to pull back things and stuff like this. So just say you can try it for yourself if you want to get familiar with this. And yeah, so what is also easy to show, or kind of easy, if you know a lot of cohomology type theory, is to show general theorems about this definition. And what was unclear for a long time, at least to me, is if you can also do calculations in some more specific internal language like ours here, where we have axioms. Can you compute the classical theorem, which says for X in a fine scheme, and N this time a bundle of weakly quasi-coherent modules, and you then compute that H1 say is 0. And this was the opportunity for us to discover Zariski local choice, or third axiom, which we haven't talked about too much, and which I will remind you of in a short time. So what this here means is that if I take this type and set truncate it, it will be trivial. And the set truncation turns some higher type into a set. And if it turns out to produce the point, which is kind of this 0 group here, then this thing has to have been connected. So what we really want to show here is that this type is connected exactly in this sense. Okay. Now I remember why I wanted to write it like this. Okay, so we want to produce exactly this for this type. Okay, so let's go. Take some element of this type and so for n equals 1. And what we need to show is it's merely trivial. So I as a function is equal to the trivial function, which sends every element of X to the point in this space, which we know we have. Okay, and there's something related we already have, and that's that at each point of X we have something connected. So that's something we can plug in here, and it means pi evaluated at X is the point. So if I slightly rewrite that one, make it absolutely clear what this is about. Then you can see what we need to do is to move the propositional truncation to the outside, but that's not something we can do in general because that's just the axiom of choice. And in this case, you can see if we had the axiom of choice in general, it would trivialize all higher cohomology of everything. So it would make using internal language of topos for cohomology boring. And what we have instead, and found for this reason, is this Zariski local choice, which doesn't give you like a complete choice, but a local choice, which means you can locally do this. To be more precise, in general, if you have some B on the scheme X, or fine scheme in this case, you have some B, which is a dependent type. So use this. There is the local choice. Says for all B like this, such that you know merely E of X for all X, like we do on the left here. There exist elements of your algebra. So also in this axiom, this is a fine, such that the standard opens for this algebra cover X. And so there exists a cover, in other words, of a specific form with local sections. So on each piece of the cover, on each EFI, I get an actual thing in here. Okay, so if I take this and apply Zariski local choice, I get the following. I get a cover. And I can forget about the exist, because in the end, I want to show a proposition. Maybe this one. So can ignore the exists. So I get a cover and some SI like this, which in our case say that chi X is the star everywhere on each DFI. So one way to frame this is we have local trivializations on a cover, but what we don't know is if they glue to a global trivialization. But we are in a very specific situation, so we kind of hope to correct them or calculate that they actually do. And in our case, we will correct them to actually match up. So now we will do the algebra that should go into a proof that this cohomology group is trivial. So we have this data, and now we can use that to pass to algebra that our module is WQC. So we know this is all taking place just in one module. So we can replace this type. No, we can't, sorry. I mean, to be able to do this, we would need something in our module here, but for now, that's just some equality type. But if we define the following, so why can I subtract here? What does it mean? Well, I have equalities and I can go them forward and backward and I can compose. So if I go Sj forward and then Si backward, I get a loop. But I think to make it a bit more instructive, I want to do it the other way. Because when no, I mean this way, sorry. Because if I go from the loop this way and then back, I have something of type star equals star. And star equals star is this group space. And we have a KA1. So it will be our M at this place X. So this is something we can do on an intersection dFi fj, where both are defined. So this is of type like this. And by going backward forward, we have something star equals star in Mx.
So this minus is just your notation for going backward. It's not the modular structure.
Yeah. So with this, I just mean in usual homotopy type theory notation, this. But yeah, okay. It's a bit justified because you work in a D-loop module. But, yeah. Okay, and for this, we know by WQC that this is M spec A, which we might want to abbreviate with M, Fi, Fj. And these have a special property, namely that Tij plus Tjk, let's maybe do it like this. Confuse myself completely. Tjk minus Tij plus Tij is 0. And why? Because when you like expand everything and calculate, you get it. And this always works when you define stuff by differences like this. So this is 0. So this means that this is a check co-cycle. And by algebra, yeah, no time for that in minus 10 minutes left. By algebra, you get that there are ui in M Fi such that Tij is uj minus ui. And the differences now, I mean, we defined the Tij as differences, so it looks like nothing from here, but the difference is that those are functions. They go to R and not to this weird equality type. And we can take stuff like this and operate on it with a function like this ui to correct it. And that should work out now up to signs. So I'll define some corrected Si to be ui plus, or let's write it on the right, make it more instructive, Si plus ui. So, or more homotopical, can go this way with Si and then loop with ui. So this is to be read pointwise as always. And then it should be possible to calculate that now either this difference or the other way around is trivial. Let's just try. So this is, these two together are Tij, and these two are, I did it right by chance, it's minus Tij. So and well, at this point we are essentially done up to some homotopy type theory reasoning we have to do. So now we know this Sij are trivializations which have difference 0 on intersections of our cover. But that means we can glue them together by some sheaf or actually stack property to get a global trivialization, which is certainly not completely clear, but that works out. So essentially we are done here and can also talk about the details at some point. Someone wants to. Guess this is a good point to stop.
So the n equals 1 came into this passage where you go from the pi type of quality types to the m spec A.
N equals 1. I mean, it. If you have a higher n, you have to deloop more times and do more stuff until you arrive at your actual module. So you get check n co-cycles. And the thing that I didn't talk about is actually the problem if you want to generalize, because that's something nobody has proven yet in hot. I think it works in this special situation, but I didn't invest time because we know the case for Hn anyway for different reasons. But this last step where you use the sheaf or stack property to glue together your local trivializations that now match, that's now something taking values in one types in this KMX once. And this level will increase, and then there's just no general lemma that tells you that you can do something like this. But yeah, I mean, in principle, it works. It just gets more complicated. And yeah, it's not completely clear that we can do an internal proof of it. Yeah.
Do you think that the following slogan is a good one? I mean, in view of our Zariski local choice, I mean, cohomology measures the failure of the global axiom of choice, and local choice allows us to actually calculate cohomology using check.
Yeah, absolutely. Or at least
or says that it is check cohomology.
The more rough slogan that choice is choice is related to cohomology is certainly good. I mean, that's the first. I mean, I guess you always need some kind of choice principle to calculate something like this cohomology groups, where I don't know how to make precise something like. No.
And then, but okay, this was a remark. Yeah, no, it was also a question. But now the actual question is: so, okay, here you restrict to evading groups. Now, if you have an R module structure,
yeah,
I mean, so so would you use the functoriality for cohomology to get some?
You mean to get an R module structure on the cohomology groups? Yes. Yeah, I mean, I haven't thought about it, but what I would guess is to make it really in a nice way, you have to talk about ring structures on those things.
But do you really have to?
I mean, probably not. That's why I said to make it really nice.
Yeah.
But maybe you can kind of just fix it by hand and yeah. Maybe someone should try it, but yeah, I didn't so far.
I mean, every ring element gives you some map from M to M. So it should give you something from HN XM to HN XM.
Yeah, so you get a map here. So I mean, you can take it as linear structure between abelian groups and try to press it through and that way. I think it's definitely possible to get the R module structure in some workable way, but it's just that nobody has tried as far as I know. So, but yeah, so far I only do it this way because it's easier. And
well, I mean, maybe it's interesting. So if you know, for example, that you're, so if you have a divisible, so say if you have a Q structure. But no, because no, I mean the rational numbers, because you know that the rational numbers by some axiom are in there.
Okay. Yeah.
You then you could say something about the non-existence of torsion cohomology groups. So it's so even if you are not interested in the Q model structure of Q vector space structure itself, you may want to do something about it.
Well, I think that could work.
All right, so I would say we meet again here at 11:15. Then we start on time this time, so that we are done at 12:15. And the next what will be yours? Yeah, and you will have more time later, so at least I mean you 5 minutes later doesn't matter, but you don't have to hurry to talk. So. And yeah, if someone would like to see more on cohomology, then please. We'll give them second talk. It's okay. I copy it in the code. I don't know that. Nee, noch nicht.